Hey everyone, today we're going to start section 2 of chapter 14, and this section is titled Work and Machines. We have not learned about machines yet, but we have hit on work, and we did that on the last chapter and the last section when we learned about work and power. So let's kind of go over back what work is. Work, we learned, is defined as the ability for a force to cause an object to move. So our equation would be force times distance would get me my work. Remember, force is given in newtons, distance in meters, and then work is going to be given in joules. We also learned in terms of work, not only does there have to be some kind of distance or motion covered, but the force has to be in the same direction as my motion. In this section, we're going to start off with a little introduction scenario. Two good friends, each one wearing her most glamorous dress, are on their way to a school dance when disaster strikes. Their car gets a flat tire. In order to fix it, they're going to have to remove the flat tire, put on the spare tire. Unfortunately, loosening the lug nuts to get the tire off and lifting the car off the ground requires a lot more force than they're able to exert with their hands. All that means is they're not able to go out there and just lift the car up. They're not strong enough. Thankfully, machines such as a lug wrench and a tire jack actually make a lot of these tasks easier. I've mentioned the word machines in this paragraph. So what is a machine? Well, a machine is a device that changes a force and often makes our ability to do work on something easier. So how do machines make work easier? Well, they do it in one of three ways. They can either change the size of the force, the direction of the force, or the amount of distance that we apply that force, or the distance over which that force acts. Before we go into a couple of examples of how these are all related, let's talk about the relationship between the size of a force and the distance. One thing to note is that typically if you exert a small amount of force, this is going to be exerted over a very large distance. When a machine is used, oftentimes this small force is converted into a larger force, and this is going to become a shorter distance. So my large distance became short. Now, a machine that decreases the distance through which a force acts is going to increase the amount of force required. So we often say if we have a small force and a large distance, these are inversely proportional. A good example that we gave is carrying in grocery bags. Say that you wanted to decrease the distance that you are carrying in your groceries. Well, that means you're going to have to increase the amount of force that you are using. You're going to have to use more force to carry more bags, and that will limit how many trips you have to take. But if you were only trying to lift a small amount of force or use a small amount of force, you can only maybe lift a couple grocery bags, and you're going to get a larger distance because of that, because you're going to have to take more trips to and from the car. I'm going to go back a slide because there's something that I forgot to star, and it's actually pretty important for you to know. It's one of our 5 main things you should take away from this lesson. And the reason I started is because we just talked about how size and distance are related. But let's see these be used in real life examples. The first example we're going to talk about is turning the jack or the tire jack handle in order to raise a car if you got a flat tire. So what a tire jack is it's this machine right here that you put underneath a car, and right here there's a handle, and he's going to crank that handle around and around. Now every time that he cranks this handle, we're covering a distance. And he doesn't have to use that much force in order to make that handle move. So keep that in mind when we go through the next part. So each complete rotation of the jack handle, he exerts a small force and he has to cover a lot of distance. He has to keep spinning that handle around and around and around. Thankfully, because of machines, that small force can become a large force, and it becomes a large enough force that's able to lift a car. While he is covering a large amount of distance, going over and over and over again in circles, this allows the car to be lifted up a short distance. In other words, each rotation lifts the car very, very small amount. If we go back to this picture, as he spins this car lifts up a tiny amount, a little bit more, each at a time. The next example that we're going to use are going to be oars that you can use to move through the water faster, whether you're in a boat, a kayak, or a canoe. With our example, it says a rower applies a large force to the oar handles, and that causes them to move a small distance. If we go back to our example, here is where he has his hands, and they're applying a force on this oar. Notice that my force has a pretty decently big arrow. So it has a big force. But the distance over here that it covers is pretty small. It can only cover the distance about the size of his arm, or his arm length. When we have that happen, the end of the oar actually is going to move through the water, and if it was originally a small distance, it's going to convert to become a large distance. So when he pulls back on the handle of those oars, it actually covers more distance. And another thing to think of is that it's going to move in the opposite direction. So here we have an example of changing the size of a force, the distance of a force, and the direction. So going back to that example, here we had a big force from a big arrow, and then down here we have a small force. The arrow got smaller. Vice versa, if we had a small distance, this actually became a large distance. Notice this big arrow. Also note that here my input distance is to the left. My force was exerted to the left. But when I look at my output, my force was exerted to the right and my oars moved to the right. So here I changed direction as well. Now that we kind of hit on machines and what does it mean for a machine to make work easier, we have to talk about a couple other things, and that is work input and work output. Let's begin with work input. Remember, work equals force times distance. So if I was looking at work input, I would have to be able to define input force and input distance. Now I'm going to define work input another way. Another way you can define work put is work put into the machine. So typically this is what you are doing for the machine. The force that you apply on the machine is called the input force. The distance is going to be the input force acts through. So how far does that input force cause it to move? And then work input is going to be that force multiplied by that distance, hence the formula. Now this is fine and dandy, but it doesn't always make sense to those who are visual learners. So let's apply these terms and give examples from a real life scenario about them. Our real life scenario that we're going to be doing is the oar. An oar is considered a machine because it reduces or helps us move through water easier. So an oar is a machine. What happens is the input force, which is the force placed on the machine, is the example here of the force the hand is putting on the oar handle. So here my input force is just you pulling on the oar. The input distance is going to be the distance that it causes that handle to move. And then lastly, work input is the work done actually to move that handle. On the other end of that spectrum, while you are putting work into a machine, well, how does that machine spit out work that's able to lift things that are super heavy or move us through the water faster? So let's talk about work output. Just like the other one, work is going to be equal to distance times our force. So let's talk about those two things. The output force is the force exerted by the machine. So you're no longer doing this on the machine. This is what the machine is going to be able to do. The output distance is categorized as the distance that output force goes through or is exerted through. And the last one is work output. This is what you're able to get out of the machine, and it can be defined and calculated by taking the output force multiplied by the output distance. Just like the last one, this is awesome, but if you can't relate it to a real-life example, what does it mean? We're going to stick with the example of our oar being our machine. Here, if I look on the other end of the oar, the part that's actually doing the work, my output force is going to be the force of the oar that exerts on the water. My output distance then is the amount that oar travels through the water. And the work done is the work able to move that water and propel the boat forward. So for our key question, how are work input and work output related for a machine? Please note that no machines are ever perfect. In the world, there is friction, and friction is just the rubbing or sliding past of two materials. And because there's some kind of friction, you have to use some of the input work that you put into a machine to be able to overcome that friction. Therefore, work done by a machine is always less than the work done on a machine, or output work is less than input work. Now, the only way to increase work output is to increase the amount of work that you put into the machine, or you can reduce your friction. The more you're able to reduce your friction, the better your work output is going to be. For example, things that reduce friction are things that are very slick and sliding, so a flat surface versus carpet. You can also add lubricants or oils such as WD-40 or gasoline to a car to be able to help it function more appropriately. Lastly, you can also change things to rolling friction because adding wheels allows things to move easier. One thing to please note is that you cannot get more work out of a machine than you put into it. So that is why work output is always going to be less. If you want good grades in the class, you have to be willing to put in the work. And that's all this is stressing. And that's the end of the lesson. I do want to go back and star a few things that I missed. So if you're one of those students who actually missed class, I want to make sure that you get all your stars. So first and foremost, I gave the first star on the machine. The second star was given here. The third star, I'm going to actually mark here because that's an important concept. The fourth star, we're going to apply here. Understanding friction is involved is important. And the last one that we're going to talk about and star is you cannot get more work out of a machine than you put in. If you put in 80 joules of work, there's no way you can get more than 80. And that's the end of today's lesson. If you have any questions, please reach out to me. And otherwise I hope you have a great day.